So I wanted to do a couple videos talking about how we can find the moment of inertia in a situation where we would need to integrate. So we've been introduced to a very general definition of the moment of inertia. And it's that it's the sum of the masses times the radius squared. Of course, where the radius is talking about how far that particular mass is from the axis of rotation. So this is a really nice, to me, like sort of a buzz phrase, at least to think about what moment of inertia is. It's the sum of the mr squares, but then of course we have to think about what that means. And it means that the moment of inertia depends on how the mass is distributed. But this particular definition really only works if we have discrete masses like a ball or a point mass or even a block that's uniform at a particular location relative to an axis of rotation. So if we had a series of objects like that that were arranged relative to a particular axis, we could use this definition pretty easily in order to figure out the moment of inertia. The problem is, what do we do when we have an object more like this, where the mass is distributed over either a line or an area or a volume? And so it's not like we have particular pieces of mass at a particular location, but we're really looking at small elements of mass that are located in some way relative to an axis of rotation. So how do we sort of transfer this definition to this situation? And that's what we want to talk about. So if we at first thought of these small little masses right here they're written as dm, but even if I sort of thought of them as like a delta m, we could sort of use this idea that the moment of inertia is the sum of delta m sub I times r sub I squared. But then you feel like when you do the delta m sub I, you're like sort of imagining that you're taking a little block of the mass and you're taking something that's very curvy and amorphous and you're trying to split it up into equal cubes or squares of mass. And that's going to give you some error around the edges, you know, so like when I take a little piece right here, you know, I'm sort of going beyond the limits or the boundaries of the object. And I know that as those masses, little blocks get smaller and smaller, my accuracy is going to improve. So what I really want to do is do the limit as delta m becomes infinitesimally small of this summation of delta m sub I r sub I squared. And honestly, that is really just leading up to the definition of what an integral is when those elements become infinitesimally small. And this ends up to be the integral of dm times r squared. So that's sort of the format of how we would define the moment of inertia for a situation where the mass is distributed over a length, a volume, an area. And in a sense, what it becomes our job to do is figure out how do I express each one of these terms in a way that makes sense for the geometry of the problem and put it in a format that's going to allow me to easily integrate. So for instance, what I want to talk about are just some of the basic ways that the mass could be distributed. And so, for instance, we could have a linear distribution of mass. And this is a situation where we would have a line. So we would have like a long line. You might think about the rod that we looked at earlier in this chapter, something like that, where the mass is distributed over a length. And typically, we use the symbol lambda. This is sort of a common notation that you'll see, that lambda would represent the mass per unit length. Now, if it's distributed evenly, so it's just really lambda can be given by the total mass over the total length, then it's possible to say that if I take a small piece of the linear distribution, like if I take a really small little piece of it that I would say had a length of dl, then I'm going to get a really small piece of mass dm. And so I could actually use this to rewrite, and this could give me a way of being able to express the dm in terms of the mass distribution lambda and then the length of that little piece. This little piece is going to have a particular coordinate associated with it. Usually it'll be like dx or dy, something like that. And then I can actually express the radius. You know, the radius will be expressed with the same units that the length is, and I'm going to get that in a format that it's going to be easy to integrate. Other possibilities is I have an area distribution. And so this is a two-dimensional object where the mass is distributed over the area. We typically use the Greek letter sigma to represent that. And so then again, the dm over dA would also have the same ratio. And so I could actually write dm could be written as sigma times dA. So I would divide up my shape into small increments of area that had a particular distance from the axis of rotation, set it up like that so I could do the integration. And finally, we could have a volume distribution. So we could have a three-dimensional object. So that our mass is distributed over the volume. Typically, we use the Greek letter rho to represent that, same as we use for density. And if it's uniform, we can just write as dm over dv. So if I take a very small piece of it that represents a small volume, I'm going to get a small amount of mass. And so this means that dm can be written as rho dv. And so how I divide up my object, I would want to choose a particular element of volume that has a constant radius from the axis of rotation so that I could easily set up the integration. So if you're kind of freaking out that this sounds like a lot and kind of complex, I want to assure you that this is just sort of information that I want you to have in the back of your mind. And in the next video, I might split it into two depending on how long it takes, we're just going to look at the really simple case of a linear distribution, which I think is really well within you know, the ability to comprehend what's going on. It's a lot easier than the more complicated area or volume. And so we'll just see how we could use the case where we have a constant distribution of mass along a line and how we could calculate the moment of inertia. And I think you'll find that it's not that bad once you see it in action. All right, thanks.